All right, this lecture is about Hardy-Weinberg Type 2 problems where we cannot assume the Hardy-Weinberg equilibrium. Generally, the first step here is we got to go find P and Q. We often have to find it directly, but you'll watch, somebody often gives us this sort of special information. Today, for example, we're at the sheep problem again. We've got 80 black sheep. We've got 20 white sheep. Now, remember, at this point, we could easily know, if we already know that black is dominant to white, right? So we know that the black ones are going to be big A, the white ones are going to be little a. That means we already know. Some of you were thinking, oh, that's Q squared. This is not Q squared. And the reason it's not is because we're not assuming Hardy-Weinberg equilibrium. So we can't do that. However, we can count the number of little a's there. That's good, but we can't solve the problem that way. So what we're going to have to do is we're going to ask ourselves, I guess the question is this population in Hardy-Weinberg equilibrium, or is there some kind of evolutionary change occurring here? Usually they'll give us this piece of information, and here's the piece of information. 20 individuals are big A, little a. So right away, we know that we have, in different genotypes here, of this genotype, and this genotype, we know that 20 are here, we know that 20 are here, and that means 60 must be here. So there we are. Now from this, we know we can calculate P and Q. These may or may not be P squared plus 2PQ plus Q squared. We can't assume they are, so let's move forward. Let's do this. In this particular case, we happen to have 100 individuals. That's handy. So you can also do this by assuming that you have twice as many individuals as you have. So let's say there are 100 individuals. There are 200 alleles. That means that from the big A group, there are 60 big A's, and there are 60 big A's, right? From this group, there are 20 big A's, and there are 20 little a's, and that's the tricky one there. And this group has 20 little a's and 20 little a's. So when we get all these added together, they will equal 200, right? So if we count the big A's, we see this many, and we count the little a's, we see that many. So now it looks pretty easy to say that 60 plus 20 is 120, 140. So P is equal to 140 over 200, and Q is equal to 20, 40, 60. 60 over 200. And 140 reduces to 70 over 100 equals 0.7, and 60 reduces to 0.3. So we've got P and Q. Now, from this point, now take a look back at what we did here. The tricky part is always doing the heterozygote here, right? That's the hard part, because that's where we have to figure out the total number. And again, what I usually do is just double whatever number is there and put that in the denominator. So this denominator happens to be 200. If it was 250, you would use 250 for the denominator. And that makes it pretty easy. If you're given percentages, then you use what we just did here. You use 200 because they would sum to 100. All right, P and Q, remember, stay the same no matter whether or not you're in Hardy-Weinberg or not. This is a constant. Like, this is just a fact, right? This is just P and Q. Now we can go back and calculate what D, H, and R would be if Hardy-Weinberg equilibrium were the case for this particular situation. This would be 0.7 squared plus 2 times 0.7 times 0.3. Gosh, these numbers are familiar. Plus 0.3 squared. 0.7 squared is 0.49 plus 0.42 plus 0.09. Wow. Okay. These should add up to 1. They're off by a little bit. I think they're not actually off at all. They're perfect. That looks great. They all do add up to 1. So these are the frequencies. That's right. These are the percentages, right? Percent for D, H, and R when you're at Hardy-Weinberg equilibrium. Let's go back and compare them to the original population here. 60, 20, 20. So 60, 20, 20 does add up to 100, so that's the same as being 0.6, 0.20. You might have to divide those to find them in the event there's not 100 individuals. And the question is, are these numbers the same? And there are some statistical tests we can do, but we don't need to do them in this class. We look at that and we say, not in Hardy-Weinberg equilibrium. So something is causing there to be more R's and fewer heterozygotes, and in fact more of these homozygous D's over here. So that is the way you solve a problem like that. Remember, the key here is don't try to jump to Q squared. Don't do that. Usually when you can't assume Hardy-Weinberg, you've got to go straight to finding P and Q.